Assalamu alaikum. Today we want to talk about chapter 13, Alkenes, Alkynes and Aromatic Compounds. Now, we studied alkanes in chapter 12 and we said that alkanes are saturated as they have as many hydrogens as possible, whereas alkenes and alkynes are unsaturated because they contain carbon-carbon multiple bonds. Alkenes are hydrocarbons that contain carbon-carbon double bonds, and alkynes are hydrocarbons that contain carbon-carbon triple bonds. Most of the organic chemicals used in making drugs, explosive, paints, plastics, and pesticides are synthesized by routes that begin with alkenes. More than 28 million tons of ethylene were produced in 2010, most of it used for making propylene polyethylene plastics. Now, naming of alkenes and alkynes. Step 1. Name the parent compounds. Find the longest chain containing the double or triple bond and name the parent compound by adding the suffix "ene" or "ine" to the name for the main chain. If there is more than one double or triple bond, the number of multiple bonds is indicated using a numerical prefix. This is an example. What is the parent? You count these 5. So the parent alkane pentane, since it contains one double bond, it is pentene. So this is a pentene. Name as pentene, 5 carbon chain. This is, if you count them, this is a 6 carbon chain containing a triple bond, so it must be hexane. Now, this one you name as hexene, a 6 carbon chain containing a double bond. You see, this is the continuous chain of carbons. We must pass through the double bond, not as heptene, although if we count from here 1, 2, 3, 4, 5, 6, 7, this is longer than this 6, but this does not pass through the double bond, so this is wrong. So this is not heptene, it is named as hexene. Step 2. Number the carbon atoms in the main chain so that those with multiple bonds have the lowest index numbers possible. Begin numbering at the end nearer the multiple bond. If the multiple bond is an equal distance from both ends, beginning numbering at the end nearer the first branch point. Here, we begin at this end because it is nearer to the double bond. So 1, 2, 3, 4, 5, 6. The other compound, we begin numbering from this end. Although this double bond is at equidistance from both sides, yani if you count from here 1, 2, 3 and if you count from here 1, 2, 3. But here we give the branch a lower number, 2, instead of giving it number 5. So we begin from this side. Now we begin at this end because it is nearer the triple bond. Here, this is 1, 2, this is also 1, 2. But since we begin with the side near the triple bond here. Cycloalkenes are quite common. The double bonded carbon atoms in substituted cycloalkenes are assigned index numbers of 1 and 2 so as to give the first substituent the next lowest possible index number. Here, do not begin here. Begin here. Numbering must go through the double bond. But what determines this? The substituent. If we number from this side, methyl will take number 5. But if we number from down top, it takes number 4. So this is better. Write the full name. Assign numbers to the branching substituents and list the substituents alphabetically. Use commas to separate numbers and hyphens to separate words from numbers. Indicate the position of the multiple bond in the chain by giving the number of the first multiple bonded carbon. If more than one double bond is present, identify the position of each and use the appropriate name ending. So if we these are the compounds that we saw before. Let's name them. So we begin from this end because the double bond here at number 1. We must give it the smallest number. So this is pentene, but it is 1 pentene. We must put 1 pentene because if this moves here, the double bond, then it becomes 2 pentene and so on. Here we begin numbering from this side. So this is 2, the parent compound hexane. It becomes hexine. Why? Because it has this triple bond. And you remember the one we said, although this one here consists of 7 carbons, but we chose this as a parent because the double bond must be we must pass through the double bond, and we start from this side to give it low number 2. But if you count from this side, you give it number 4. So now what is the substituents? At number 3, this is in red, propan. So when you remove one hydrogen, it becomes propyl. So it is 3 hyphen propyl hyphen 2 hyphen hexene. And here again, this compound, we said we begin numbering from the side that is near to the triple bond, and this is a substituents and number 7 hyphen methyl hyphen 2 hyphen octane. Now this is an example of a compound with 2 double bonds. Notice here how we will name this. Suppose we do not have this, omit this. Suppose we have this only, then we call this 1,3, the parent compound buta, and then di and ene for the double bond. But if we have a substituent here, we begin numbering from this side, and we say 2 hyphen ethyl hyphen 1,3 butadiene. Whereas for this compound, we begin numbering from bottom here 1, 2, 3, 4 to give the methyl small number. Because if we number from this 1, 2, 3, 4, 5, it gives it higher number. So no, it is 4 hyphen methyl cyclohexene. Here there is no numbering for it, because if you remove the methyl, then this is called cyclohexene. It is known. We do not give a number for the double bond as we did here, because cyclohexene is 1, whether the double bond is here, here, it always takes number 1. So we put the position, the number of the substituents for methyl cyclohexene. Common names. For historical reasons, there are a few alkenes and alkynes whose names do not conform to the IUPAC rules. The 2-carbon alkene should properly be called ethene, but the name ethylene is accepted by the IUPAC. Here the IUPAC is an abbreviation for the International Union of Pure and Applied Chemistry, where all the rules for nomenclature are set there. The 3-carbon alkene propene is usually called propylene. The 4-carbon diene 2-methyl-1-tribute is more commonly known as isoporine. The simplest alkyne should be known as ethine, but it almost always called acetylene. So note these common names for some alkenes and alkynes. Now, section 3, the structure of alkenes, Cis-Trans isomerism. Now the 2 carbons and 4 attached atoms that make up the double bond functional group lie in a plane. There is no rotation around a double bond and the molecules are more rigid. Now if we take, this is the environment of the double bond, carbon-carbon double bond. We said this carbon will have 2 substituents and this carbon will have 2 substituents. These are the ends and these are the sides. However, it's always, there is no rotation around the double bond. It's rigid. Now, if we have this example, a butene, 2-butene, and if you put it in a straight chain way, it is called 2-butene. But if you arrange, if you draw the alkane in this way, you see, if you draw it this way, and the 2 methyl groups, these are on the same side of the double bond, this is given, this means together. However, if the 2 substituents are opposite to each other, means trans means opposite. And you can look at the model here. You see, 2 methyls cis, 2 methyls trans. So this is called Cis-Trans isomerism. Now, if we take this example, does this alkene 2-methyl-1-butene has cis-trans isomers? You draw it. You draw the double bond. It is at position 1. Then this is 1, 2, 3, 4. And at position 2 we have methyl. This is the substituent. So the double bond, this carbon has 2 hydrogens. And this carbon has 2 different groups, ethyl and methyl. But since these 2 compounds are identical, because the carbon left of the double bond has 2 hydrogen atoms attached, cis-trans isomerism is impossible. Here, because these 2 are identical, this compound has no cis-trans isomerism. However, if we take this compound called 2-pentene, and we draw it in this way, this is the double bond, this is carbon 1, 2, 3, 4, 5. And this is the position of the double bond, 2-pentene. But here this carbon has 2 different substituents, and this carbon has 2 different substituents. So cis-trans isomerism is possible. So since these 2 larger substituents are in the same direction, this is called cis-2-2-pentene. When these are put opposite to each other, then this is called trans-2-pentene. These 2 compounds are not identical. Neither carbon of the double bond has 2 identical groups attached to it. So cis and trans compounds are different from each other. Some properties of alkenes and alkynes. Nonpolar, insoluble in water, soluble in nonpolar organic solvents. Know these: less dense than water, flammable, chemically reactive at the multiple bond. Memorize these properties. Most of the reactions of carbon, and now reactions of alkenes and alkynes. Most of the reactions of carbon-carbon multiple bonds are addition reactions. A generalized reagent XY adds to the multiple bond to yield a saturated product that has only single bonds. Here you have, if we add XY through this double bond, we have this two single bonds form. So this bond breaks, and these two bonds form. This is called an addition reaction. So alkenes undergo addition reaction. This is the meaning of addition. Addition of hydrogen to alkenes and alkynes is referred to as hydrogenation. Alkenes and alkynes react with hydrogen in the presence of a metal catalyst to yield the corresponding alkane product. Here we have an alkane plus hydrogen in the presence of catalyst and alkane, and alkyne plus 2 H2 in the presence of catalyst, we have alkane again. This process is used commercially to convert unsaturated vegetable oils to saturated fats used in margarine and cooking fats. This is called again hydrogenation. Addition of Cl2 and Br2 to alkenes and alkynes. Now, also we can add halogen. This X could be Br or Cl, and the product we get a 1,2-dihaloalkane. Now, bromine can be used as a test for multiple bonds and unsaturation of fats. If we add a few drops to a sample of an unknown compound, if the color of bromine is known as to be brown, if there is an immediate disappearance of the color, this indicates the presence of a multiple bond, as the bromine reacts to form a colorless dibromide. So this is a chemical test to distinguish between alkene and alkyne, for example. If you add drops of bromine to an alkene, the solution is colorless. But if you add it to an alkane, it becomes colored. So this is a test to distinguish between them. Now, what about addition of HBr and HCl to alkenes? Now, alkenes react with hydrogen bromide to yield alkyl bromides, and with hydrogen chloride, HCl, to yield alkyl halides, chlorides. This is called hydrohalogenation reactions. So, if you have a double bond, we can add HBr or HCl to the double bond. If we add HBr, we get an alkyl bromide. If we add HCl, we get an alkyl chloride. As simple as that. Now, the addition of HBr to 2-methylpropane is an example. Take this example. This is called 1, 2, 3. So at position 2 we have methyl. So this is called 2-methylpropane. Here again we do not put 1 propane, because propane, whether you put the double bond here or here, it is a number 1 plus HBr to produce this 1, 2, 3. Now here at position 2 we have 2 substituents, brom and methyl. We give them alphabetical priority in naming. So 2 hyphen, we start with the bromo, 2 hyphen methyl, and the parent alkane is propan. Only one of the 2 possible addition products is obtained. 2-methylpropane could add HBr to give 1 bromo, 2-methylpropan, but it does not. It gives only 2 bromo, 2-methylpropan as the major product. And we notice that in this reaction, hydrogen is added to this carbon, number 1, and Br is added to this carbon. We have only 1 product, not 2 products, because there is a rule. There is a rule for adding. This rule is called Markov-Nikoddy's rule. Now, in the addition of HX, the HBr, to an alkene, the major product, this is called the major product, arises from the hydrogen attaching to the double bond carbon, which means this, that has the larger number of hydrogen atoms. Then HBr consists of H and Br, where H added to this carbon because it has the larger number of hydrogens, and Br is added to the other one. Even no hydrogens on this carbon, so Br attaches here, and we get this only one product. Now, if an alkene has equal numbers of hydrogen atoms attached to the double bond carbons, symmetrically substituted double bond, both possible products are formed in approximately equal amounts. Now, if we look at this alkene, we notice that the double bond, this carbon has one hydrogen, this carbon has one hydrogen. So H can add one time here and one time here, and Br can be attached one time here and one time here. So we get a mixture of two products in a 1-to-1 ratio. One is called 3-bromopentane and the other is called 2-bromopentane. So this is the case when you can get a mixture of the products when the two carbon of the double bond has the same number of hydrogen atoms attached to it. What about addition of water to alkenes? This is called hydration. An alkene will not react with pure water alone. If a small amount of a strong acid catalyst is added like H2SO4, an addition reaction takes place to yield an alcohol. So if you have, for example, ethylene plus water in the presence of H2SO4 as a catalyst, we get ethyl alcohol. Now, Markov-Nikov's rule can be used to predict the product when water adds to an unsymmetrically substituted alkene. Again, suppose water dissociates into H plus and OH minus. According to Markov-Nikov rule, H plus must be added here to this carbon because this carbon has two hydrogens. So H will be added here, this is, and OH will be added here because there are no hydrogens at all. So this is the product that is produced, 2-methyl-2-propanol. No, this reaction. And this is the mechanism of the reaction. Now again in step 1, HBr dissociates into H plus Br minus, then the double bond here attacks, it's a nucleophile, attacks to, it abstracts this electrophile and you form this compound. This is the positive charge because this now this abstracts and this becomes positively charged, and then this is an intermediate, then Br minus attacks the carbocation. This is called a carbocation. Now any species with positive charge here in organic chemistry, it's called carbocation, and then you have this product bromoethane. So this is the mechanism, 2 steps, step 1, step 2. In step 1, the double bond abstracts the proton here to form a carbocation. This is called generation of carbocation, then attack of the nucleophile to form the product. How addition reactions occur? The more carbons attached to a carbocation, the more stable it will be, making its formation more favorable. Tertiary carbocations are more stable than secondary, secondary more stable than primary, primary are so unstable that they almost never fall. This provides the scientific basis for Markov-Nikov rule. So the major product arises because the intermediate it is derived from is more stable than any other intermediate. Description of the individual steps by which old bonds are broken and the new bonds are formed in the reaction is called the reaction mechanism. As I told you, this is reaction mechanism. Bonds are broken and new bonds are formed. This is known as the mechanism of the addition reaction. Now, aromatic compounds and the structure of benzene. Aromatic, the class of compounds containing benzene-like rings. So, this is called the Kekule structure of benzene. You see here we have the double bonds are at positions 1, 1, 5 and 3, or 1, 3, 5 this way. These are two equivalent structures which differ in the position of their double bond electrons. Neither one is correct by itself because these pi electrons, they keep moving and they form a cloud above and below the plane of the benzene ring. So the correct structure of benzene is this, where we represent the pi electrons by this circle, meaning that the 6 pi electrons, they form a cloud, electron cloud above and below the plane of the ring. Benzene is a flat, symmetrical molecule with the molecular formula C6H12. Benzene and other aromatic compounds are much less reactive than alkenes, and they do not undergo addition reactions, as we will see. Again, benzene and other aromatic compounds are less reactive than alkenes. They do not undergo the so-called addition reaction we described for alkenes. The double bond electrons are free to move over the entire ring. Each carbon-carbon bond is intermediate between single bond and a double bond. The name resonance is given to this phenomenon. So again, these are two resonance structures, and it's represented by this. Polycyclic aromatic hydrocarbons are substances that have two or more benzene rings joined together by a common bond. One is called naphthalene, this is anthracene, this is phenyl 3. Substituted benzene are named using benzene as the parent. No number is needed for mono-substituted benzene because all the ring positions are identical. For example, if we place bromo here, we do not give it a number. This is called a mono-substituted benzene. Simply bromo followed by word benzene. If the substituent ethyl, it's ethyl benzene. If it is nitro, nitrobenzene. So there is no number is needed here. Now, di-substitute benzene are unique in that the relational descriptors we have ortho, meta, and para may be used in place of 1, 2, 1, 3, and 1, 4. The terms ortho, meta, or para are then used as prefixes. For example, if you have this di-substituted benzene with two similar brom, you number 1, 2 dibromobenzene. But what is the relationship between them if we consider this position? Position 2 is ortho to 1 and 1 is ortho to 2. So instead of putting 1, 2, we put ortho dibromobenzene, ortho shahta, or simple O. Now, the other position, 1, 3, this is referred to as meta. So, we said we have two substituents, chlor and nitro. So, we arrange them alphabetically. Meta, we start with the chloro, then nitro, benzene, or simply M, كذا. Now, if the two substituents are opposite to each other, this is a para position. So, 1,4-dimethylbenzene, it becomes para-dimethylbenzene or P-dimethylbenzene. Naming aromatic compounds. Now, many substituted aromatic compounds have common names in addition to their systematic names. For example, methylbenzene is known as toluene. You see this structure in blue without Cl, this is called toluene or methylbenzene. This one without the nitro, if there is OH on the ring, this is called phenol. If you have an H2 on the ring without this Pr, then this is known as aniline. Then if there is a second substituent, you name it according to the parent name. This is Cl. What is the relation of Cl to the methyl? It is in a para position called para-chlorotoluene. Now, the NO2 is in a meta position, 2OH, meta-nitrophenol. Now, the Br is in an ortho position to the NH2. It's called orthobromoaniline. Naming aromatic compounds, again, the benzene ring itself may be considered a substituent group attached to another parent compound. As we said, the formula for benzene is C6H6. But if we replace one hydrogen like this with anything, or this is attached to this, for example, now this becomes a phenyl group. This is called a phenyl group here. Now in this compound, now the benzene is a substituent or a branch. So we count from this side 1, 2, 3, 4, 5, 6, 7. We do not count from this side 1, 2, 3, 4, 5. We want to give this a smaller number, 3. So 1, 2, 3, 3. What is in position 3? Phenyl. So 3 hyphen phenyl. And what is the parent compound? 7 heptane. What is the parent compound? It's called heptane. Reactions of aromatic compounds. Aromatic compounds usually undergo a special type of substitution reaction known as an electrophilic aromatic substitution reaction. Remember, we said alkenes undergo addition reaction, whereas aromatic compounds undergo substitution reaction, specifically electrophilic aromatic substitution reaction. A group-wise substituent for a hydrogen on the ring. It does not matter which of the ring hydrogen is replaced because all are equivalent, and the mechanism responsible for this type of reaction is similar to that seen for alkenes. Some examples on electrophilic aromatic substitution reactions are, for example, when you place NO2 on a benzene ring, this is called nitration to form nitrobenzene. If you put X, or if you attach X or substitute one of the hydrogen by X, this is called halogenation, where this X could be Br, Brom or Chlor. However, if you substitute one of the hydrogens on the benzene ring by this group called SO3H, then this is called sulfonation. So sulfonation refers to the substitution of a sulfonic acid group for a hydrogen on an aromatic ring. Thank you. This is the end of this chapter 13.